Z on the edges, and nothing on the face. So you can check that. So this polygonal groups is non-positively curved in a certain sense of Gersten installing. So kind of a black box. It's the theory of complexes of groups. What it means is that this Higman group for n equals at least 4, and here I'm gonna focus on n at least 5. Hn acts on a cat 0, actually cat minus 1, n-gonal complex, and such that with strict fundamental domain a polygon, and such that if you focus on such a fundamental domain and you look at the diagram of embeddings of stabilizers of faces, maybe stabilizer of the face, stabilizer vertex, stabilizer of an edge, and look at the various diagram that you get, then that diagram is isomorphic to this diagram of PS12. So in particular, from the local viewpoint, that action is very well understood. You really understand very well those embeddings. So in one case, it's going to be the embedding of the stable lever, so it's quasi-isometrically embedded. In the other case, it's like distorted. In particular, it's very simple to check that this action satisfies the weak, or that weaker form of asymmetricity at r equals 0. I won't have time to detail that. It's a very simple exercise. In particular, it means that the action is on that complex Sn is acylindrical. It's an n-gonal complex where you can easily subdivide it into a cube complex, into a square complex. Yes. So it's acylindrical. Okay, so the acylindrical hyperbolicity of the Higman groups were already known, was shown by Nasayan and Ozin, but actually having a concrete example of an acylindrical action on a hyperbolic space allows you to get more. So maybe a couple of consequences using the dynamics. Some are straightforward. For instance, you can get a strong form of the cis alternatives of the groups. So here a subgroup is either, so a non-mutually cyclic subgroup either embeds in BS12, so stabilizes a vertex, or is asymmetrically hyperbolic, in particular contains F2. You can also use the action to construct exotic quotients using small constellation arguments. So in particular, you can show that the group, the Hn is residually F2 free, so free, meaning that every element of the group survives in an infinite quotient that does not contain a single copy of F2. And maybe a more surprising result is a complete understanding of the endomorphisms of the Higman groups.
The bounds of solitary group is not residually cyclic, right? So how is the whole group is bounds of solitary group at group 3?
Yes. BS12 is yes.
Yes.
Sorry.
Yeah.
So yeah.
So what happened to bounds of solitary group?
They survive. So you're really gonna kill. So you list all the loxodromic elements for that action, and you're gonna kill successively powers of loxodromic. So you're gonna start with H1, kill H1 to the power something huge, so that you can apply the Maniga, the Lozin since the vertex stabilizer does not contain F2, you can show that the group that you get, the limit group that you get is really F2, F2. So you do nothing at the level of the vertex group. So all those long stacks are surviving in that portion. And so maybe one last consequence. So the endomorphisms and the automorphisms of the Hickman group. So we've got a very strong form of the Hopf and the co-Hopf property of the group. So that every non-trivial endomorphism from Hn to Hn is an automorphism. So as soon as something is not killed, then you're automatically an automorphism. So it's an extreme form of being Hopfian and co-Hopfian. And you also understand the automorphism. You just split as the semi-direct product of Hn, so the inner part, and the copy of Z and Z, which corresponds to permuting cyclically the generator. And that's sort of result that parallels what is known for mapping class groups out of FM. So it's that action is some sort of like a cousin of the action of mapping class group on the curve complex. Okay, so when did I start? When
Finishing up next week. We started out.
okay. Okay. So I won't have time to talk about to give many details about the rest. So that was one case using the combinatorial geometry of the space to show that the eccentricity and other conditions are equivalent to a much weaker form. But in space which are non-locally compact, you can also have some extreme phenomenon like the following. So you can impose that there exists a finite subset of your space such that the following occurs. If you look at the G orbit, so you want to construct some element, strongly contracting element satisfying the WPD as before to show that your group is asymmetrically hyperbolic. And in some case what's going to happen is the following. If you look at the G orbit of S, so the following is going to occur. If you look at 2 points which have projections on those on this orbit that are extremely far apart, then not only are you gonna like in the strongly contracting case be very close to that orbit for a very long time. That's something we already know. But you can also force the area geodesic from X to Y to meet all of them, apart from maybe there's some error as usual, maybe sort of hyperbolic thing. So it's a much stronger notion of strongly contracting element, or something which I call a Uber contracting element. So it seems a bit too strong. It seems hard to believe that we can force really all the geodesics to go through lots of translates of S. But actually you've got many cases where such a phenomenon can occur. For instance, in cat-zero Q complexes, using the Kapra-Sagiev machinery of skewering and all that. So in particular, in such cases, whenever that machinery is available and using also results of Chatterjee, Furnos, and Yossi, you can show the following instance, which is common with you and myself. So if you have G acting, so I'm not going to do the optimal case compactly on an irreducible cat-zero Q complex. So for people who are used to that, you can replace that by essentially without fixed point by infinity. If the action satisfies, so it's what's called weakly cylindrical, so that weakening at r equals 0. So if you're far apart, then the intersection of pointwise stabilizers is trivial. Then your group is either virtually cyclic or acylindrically hyperbolic. And also, as a bonus, every hyperplane stabilizer is weakly non-normal, meaning that it intersects some conjugate along a finite subgroup. So for instance, you can use this to recover like a purely geometric proof of the cylindrical velocity of the human groups. So the original proof by Vincennes and Ozin was basically something similar for actional groups. If you have actions on trees, say for an amalgam, if the edge group is weakly mononormal, then some extra conditions, then your group is acylindrically hyperbolic. But to check that that edge stabilizer is weakly mononormal is a bit painful. It's really you have to deal with the presentation of the group and play around with it. Here, it's much more simple. Okay, so it's a bit more involved, but it's purely geometric, and you can really see geometrically why this group is acylindrically hyperbolic. And I won't have time to detail the rest. We can also use those ideas of Huber contracting elements, for instance, to show the acylindrical hyperbolicity of some subgroup of the Kremlin group in dimension 3, which was studied recently by Lizzie, Furter, and Lamy. And so that's the group of chain automorphisms of SL2C, which is acylindrically hyperbolic.
Axes that you could really force a geodetic to go along. And when you have this picture you put on the right hand board where you can reduce something into some nice finite case is when X is a non-spherical building.
Yes.
And then where you've got 2 points, so as long as so you need a slightly stronger condition, you need the orbit of H not only to be strongly contracting but also not within that neighborhood of a wall, say this apartment. Then you'll get an incredibly similar picture to what you've got here, except it will really actually sort of sit inside the apartment, sit inside one apartment for a very long period of time. And you get exactly the picture you drew on the right, but you end up with this geodetic companion inside the apartment, so it's proper neighborhood. So, and you don't even need the building to be hyperbolic.
Yes, yeah, that's also something for this Weber contracting. So here I've given an example in Q complex here, but you can construct Weber contractions whenever you've got a group acting on some complex such that some vertex has a stabilizer which acts with unbounded orbit on some link. And there's a very weak non-positive curvature assumption which works, for instance, for Cat-zero spaces, small concentration complexes, systolic complexes, also for hyperbolic complexes, which satisfy some geometric inequality, not necessarily linear, just some function. Yeah, so you can really, whenever you're in a non-locally compact case with some nice local behavior, you can reconstruct also many constructions, like strong, like fewer constructions like that.
So in this theorem, is the so X dimensional?
Oh, sorry, yes, yes, yes. Yeah, you need
So the reason I asked was because I think the fact that every time points that was taken by one was also, I think, something that was something I did with.
So say it again.
So you know the fact that stabilizers working by normal, I think this is also something which follows from recent year in my digital system.
Okay.
But probably this is a different method.
Okay.
But you do need finite dimensional?
Yes, we do. Like, so here is included the
Oh yeah,
compacting,
you're saying co-compacting.
but yeah, otherwise what you need is the characteristic AF setting. So
Yeah.
finite dimension